Loading and exploring bank datasets. In this lesson, we will learn how to load and explore real banking datasets with Python. Bank datasets are crucial for understanding customer behavior, detecting fraud, and managing risk. You will build skills to read datasets, understand structure, spot problems, and prepare for real analysis. We will use practical examples you could face in a real bank data science job. Running the cell now. We import pandas so we can work with tabular data as data frames. We import NumPy for numerical operations and generating random numbers. We import the warnings library to handle unnecessary warning messages. We ignore all warnings so notebook output is clean and clear for learning. Running the cell now. Practice, try running just the pandas import line and see if there is an error. If you have trouble with any import, search for solutions on YouTube or official docs. Understanding banking data structures. Banking datasets are usually tables with rows for transactions, accounts, or customers. Columns describe each row, like amount, type, customer ID, or date. Data might be synthetic or real, but structure is similar in practice. Beginners often confuse row meaning or misuse data types, for example, dates as strings. Missing or invalid data, duplicate rows, and mixed column types are common mistakes. Running the cell now. We will build a simple synthetic banking transactions table. We are adding a comment to describe what this section is doing. We set C to 42 for reproducibility so results are the same each run. We define how many transactions we want, in this case 1000. We set the number of bank customers as 200. We start building the data frame for transaction records. Transaction IDs count from 1 to the number of transactions. We randomly assign customers to each transaction using unique customer IDs. We create a transaction amount using normal distribution around 150. We randomly label each as debit or credit. Every transaction has a channel like ATM, online, branch, or point of sale. Each row gets a different hourly timestamp starting from January 1st. Our data frame is now done. Let us print the shape to see how many rows and columns we have. Now let us see a few sample transactions at the top. Running the cell now. The output shows a synthetic banking transactions dataset with 1000 rows and 6 columns, reflecting typical transaction details such as IDs, amounts, types, channels, and timestamps. Notice the mixture of data types, numerical amounts, categorical transaction types, and date-time values, illustrating how structured banking data captures multiple aspects of each transaction for analysis. This aligns with the lesson's goal of understanding the meaning behind rows and columns in banking datasets. Can you spot the columns for the channel or transaction_type in the output? Watch on YouTube for a video demo on how to synthesize your own datasets. Search Python Bank Data Generator. Let us now build a sample table for customer details. We describe what we are about to do. We create a list of customer IDs, one for each unique customer. We assemble the data frame where customer is the key column. Each customer gets a unique customer ID. Assign the first 150 as retail and the last 50 as business customers. First 100 are metro region, next 100 are regional. Our table is ready. Let us check the shape, how many customers and columns. Let us preview the first 3 rows to understand the structure. Running the cell now. Here, the output shows our customers table has 200 rows and 3 columns, customer_ID, segment, and region. Notice how the segment and region columns categorize customers into groups like retail vs business and metro vs regional. This structure is typical in banking data, helping us organize and analyze customer profiles effectively. Practice, how many customers are labeled as business in this table? Look up any unfamiliar term using your favorite YouTube channel for beginner data analysis. A bank also tracks different accounts per customer. Let us create an accounts table. We describe what we are doing in this example. We set the random seed again to ensure repeated results. We build a data frame for account records. We assign unique account IDs with 5-digit codes. We use the same customer IDs as before so every account belongs to a customer. We pick an account type randomly, savings, check, or credit. Open dates are spaced 30 days apart starting from 2015. Our table is built. Now we print the shape to see total accounts and columns. Finally, we preview the top 3 accounts. Running the cell now. The output confirms the creation of a synthetic accounts table with 200 rows and 4 columns, representing individual bank accounts. Notice how each row links an account _ID to a customer _ID, specifies their account _type, savings, check, or credit, and records an open _date as a proper date time, highlighting correct data types and the relational structure between customers and accounts. This example reinforces the foundational concept of banking data organization, where each row is a unique account described by key attributes. Try changing the starting date or the number of accounts. What do you notice? Let us try reading a real-world banking risk table from the web. We describe what we are doing in this section. This is the direct web URL for the German credit dataset from the UCI machine learning repository. We define the column names for all features and the final loan outcome. We read the dataset into pandas, using spaces as column separators. If credit _status is 2, we mark it as default by setting a flag. Check the size and dimensions of the loaded data frame. Show a quick preview of the 2 label columns. Running the cell now. This output shows our loaded dataset has 1,000 rows and 26 columns, matching the expected structure with 24 features plus 2 target columns. However, the first 3 rows in the credit _status column are nan, indicating an issue with how the data was read, most likely due to incorrect parsing of the space-separated file. This highlights the importance of carefully inspecting data types and column values when working with banking datasets to ensure meaningful analysis. Challenge: how many records are labeled as default? Use some credit _df, default _flag. Next, let us load a well-known credit card fraud detection dataset. We announce what data we are loading. This is the storage URL for the TensorFlow credit card fraud dataset. Load the CSV using pandas. Show the total number of rows and columns. Display the top 3 transactions for review. Running the cell now. This output shows the shape and first few rows of a credit card fraud dataset, with 284,807 transactions and 31 columns describing each one. Notice the mix of anonymized features, V1 to V28, a time column, transaction amount, and a class label indicating fraud, 0 equals non-fraud, 1 equals fraud. This verifies the dataset structure, helping beginners see how real banking data organizes many detailed features per transaction. Notice any oddities in the variable names or data range in this dataset. Basic data checking is your first job when loading any new banking dataset. Explain that we are about to check the loaded data for structure and quality. Print the data types for each column, numeric, object, or date time. Count missing values in the first 5 columns. Print some basic descriptive statistics for a sample of the columns. Running the cell now. This output shows that all columns in the fraud dataset are numeric, mostly floats, which is typical for transaction data transformed for modeling. There are no missing values in the first columns checked, reassuring us that the dataset is clean for analysis. The summary statistics reveal the scale and distribution of features like timing and anonymized variables V1 to V4, helping us understand their range and variability before further processing or modeling. Try calling fraud_df.info to see deeper information about the data frame. Unique values help us inspect what types a column can take and spot oddities. We will see all channels used in our synthetic transactions. We count how many transactions are debit versus credit. Running the cell now. The output shows the unique channels where transactions occurred: ATM, POS, online, and branch, highlighting the different ways customers interact with the bank. The transaction underscore type counts reveal nearly equal numbers of credit and debit transactions, which helps confirm the balance and validity of the dataset. This exploration is crucial for understanding the categorical variables and ensuring correct interpretation of transaction contexts in the banking data. Could you create a similar count for a region in the customers table? Bankers often search for large, unusual, or risky transactions. We filter our transactions for those that are credits at ATM channel and amount above 300. Show the shape of this filtered data frame. Preview important columns of the first few matching rows. Running the cell now. Here, the output shows that only one transaction matches all criteria: a credit over 300 made at an ATM. Notice the shape, 1, 6, confirms there's just one such row with 6 columns, reinforcing how filtering narrows down the dataset to relevant data. This helps illustrate how we use multiple conditions to pinpoint specific transactions in banking data. Can you adjust the filter for debit transactions at branches above 200? Analysis often means combining transactional data with customer characteristics. We join our transactions with customer data on the customer underscore ID key. Now we quickly print a preview to see new columns like segment and region for each transaction. Running the cell now. This output shows the first 3 transactions merged with customer details, adding the segment and region columns. Notice how each transaction row now includes customer classification, helping us combine transactional and demographic info to analyze banking behavior by customer segments and locations. This highlights how merging tables enriches data for deeper insights. Try using .merge, how equals inner, and see if results differ. We will now summarize statistics for each customer segment. We group all transactions by customer segment, retail or business, then calculate counts, average, STD, minute, and max amounts. Print the grouped statistics to the screen. Running the cell now. This output summarizes transaction amounts grouped by customer segment, showing key statistics like count, average, and range. Notice that count tells us how many transactions each segment has, while the mean and STD reveal differences in typical transaction size and variability between business and retail customers. This reinforces how grouping helps us understand data patterns within different categories in banking datasets. What do you notice about debit versus credit amounts in each segment? Let us find out which customers only use one type of account. Count how many unique account types each customer has. Filter just for those with one unique account type. Print the number of such customers. Show a sample of their IDs. Running the cell now. The output shows there are 200 customers who have exactly one unique account type, confirming these customers hold a single type of account each. Notice the shape, 200, indicates the count of such customers, and the head previews individual customer IDs paired with the value 1, meaning one account type per customer. This helps illustrate how grouping and counting unique values reveals customer account diversity in banking datasets. Can you check what regions these single account customers come from by merging with the customers table? Dates often need parsing to date-time format for analysis. Convert the date column in our transactions to pandas datetime if not already. Sort all transactions by date and reset the index to match. Preview the top 3 sorted transactions. Running the cell now. Here, the code converts this date column to a proper datetime format and sorts the transactions chronologically. Notice how the earliest transactions now appear first, with timestamps increasing by hour. This step is crucial to ensure accurate time-based analysis and avoid errors from treating dates as plain strings. Think, why is date order often important for time series or fraud analysis? Duplicated transactions can signal errors or potential fraud. We check for duplicates by matching various columns. Display the first few possible duplicate transactions. Running the cell now. This output shows an empty data frame, meaning no duplicate transactions were found based on matching customer ID, amount, date, and transaction type. This confirms that each transaction in the dataset is unique across these key details, which is important for maintaining accurate banking records and avoiding erroneous data duplication. Hint: try.duplicated, keep equals false to mark all copies, not just the second or later. Missing data can cause calculation errors if not handled. We copy our credit card fraud dataset as an example. Insert a missing value into the first amount row to simulate real-world cases. Fill missing amounts with the average amount as a quick solution. Now print some filled example rows. Running the cell now. This output shows the amount column after replacing a missing value with the column's mean, preserving the data's numeric type. Notice how the first value, originally missing, is now filled with the average transaction amount, which helps maintain consistent and usable data for analysis in banking datasets. This step is crucial to handle incomplete data without distorting overall trends. Practice: try using median instead of mean for filling in missing values. Let us show how to handle common file loading errors. We use a try except block as a safety net. Try loading a file that does not exist. If there is a file not found error, catch it here. Print a friendly error message for the user along with the exception details. Running the cell now. Here, the output shows a clear error message when the code tries to load a CSV file that doesn't exist. This demonstrates how to catch and handle file-related errors gracefully, which is important when working with banking datasets to avoid crashes and guide users to correct file paths. Noticing this helps ensure your data loading steps are robust and ready for real-world use. Use try except when reading files you are not sure exist, especially with real client data. It is good practice to check data types before running calculations. Check if the amount a column is numeric using NumPy subtype test. If not numeric, print a useful warning. If condition is not met, print nothing here. If it is numeric, notify the user that calculation is safe. Running the cell now. This output confirms that amount column is stored as a numeric type, which is crucial before performing any statistical analysis or calculations. In banking data, ensuring numerical columns like transaction amounts are correctly typed prevents errors and misinterpretations. This check reinforces the lesson's focus on validating data types to maintain data integrity and analysis accuracy. Try changing the D type of amount to a string and see if your check still works. You should avoid changing your original data by working on a copy. Make a copy of your transaction table so the original is preserved. For demonstration, adjust the amount values slightly to simulate processing. Show a few updated example rows. Running the cell now. Here, we see the first three values of the amount column after increasing each by 10%, confirming that the code correctly modified the copy without changing the original data frame. Notice the clear numeric format and that only the copied data is adjusted. This highlights the importance of copying data to avoid unintended changes when processing banking transaction amounts. Keeping a backup copy lets you debug or rerun analyses if anything goes wrong. A quick summary across all fields shows types, missing data, and spread. We use pandas describe with include all columns for a wide summary. Show the summary transposed for easier reading. Running the cell now. This output provides a comprehensive summary of the banking dataset, revealing key details about each column's entries. Notice the 1,000 rows for all columns, confirming no missing data, while unique counts like 198 customers and 2 transaction types highlight categorical diversity. This broad summary helps us quickly understand data structure and guides proper handling of numeric versus categorical variables in banking data analysis. You can also try describe on merged customers or accounts for quick data profiling. Now let us solve a realistic banking task, flagging unusually large transactions by segment. First, compute the mean and STD deviation of amounts for each segment. Join those statistics to each transaction. For each row, flag as risky if above 3 standard deviations from mean. Print examples, see which transactions are marked risky and the relevant stats. Print a count of how many risky transactions the rule found. Running the cell now. This output shows transactions labeled by segment, with their amounts compared to segment-specific mean and standard deviation values. Notice how the code flags only transactions exceeding the segment mean by 3 standard deviations as risky, resulting in just 1 risky transaction overall. This highlights how grouping and statistical thresholds help identify outliers in banking data while maintaining the context of each row segment. Practice. Try modifying the rule to use 2 STD deviations instead of 3. How does the risk count change? Keep building. Ready to try more? Search YouTube for Python Pandas banking data analysis for hands-on videos. To keep your skills sharp, try building your own synthetic financial dataset and share your work online. Running the cell now. Finding columns with a certain word helps you quickly locate features for analysis. Create a list comprehension that finds all columns containing a flag in their name. Print the list of matching columns. Running the cell now. Here, the code searches the merge data frame for any columns containing the word flag and prints the list of matches. The empty list output tells us there are currently no columns with flag in their names. This confirms that before adding any flag type indicators, the dataset lacks such categorical flag features, helping us plan the next steps for feature engineering. You can repeat this pattern for amount, date, or any other term. Summarizing transactions by month is key for seasonality and reporting. Create a new column extracting the month from transaction dates. Print the count of transactions for each month. Running the cell now. This output shows the count of transactions grouped by month, extracted from the date column. Notice how January, month 1, has significantly more transactions, 744, compared to February, 256, indicating the dataset may span only these 2 months or has a higher activity in January. This helps us practice date-time extraction and aggregation, key skills for analyzing time-based financial data. Practice. Try extracting hour or day of week instead. Exporting your clean data makes it available for sharing or further analysis. Save the merge data frame with customer segments to a CSV file. Print success confirmation. Running the cell now. Here, the code saves the merged banking dataset, including transaction details and customer segments, to a CSV file for future use or sharing. Notice that index equals false keeps the file clean by excluding row numbers, making it easier to work within other tools. This step is key in practical data analysis, as it preserves your work and supports seamless collaboration or continued exploration. Now opening the exported CSV so you can examine the combined dataset outside of Python. Now you can open this CSV file in Excel or another tool for additional review.